so far,
Professor Riccardo Di Roberto will present from
problem.
G.A.U.S. company.
Okay,
Will present
there are, for instance, if your problem
a dual
has
sensing
a
virtualized CubeSat constellation for
solution,
observation.
like a perfect cubic solution,
But you don't know what the solution is?
exactly. So if your problem has a perfect cubic solution and you choose monomial, you capture perfectly.
So, hello
If
everybody,
you use a
I'm
different,
Riccardo Di Roberto, I'm an astronautical
Fourier,
engineer
you need a
at
lot
G.A.U.S.S,
of
and I work on space systems
basis function
for
in order to
G.A.U.S.S.
capture.
Let me do a brief introduction of G.A.U.S.S.
So there are bad ways.
G.A.U.S.S is an Italian
Look at the
private company,
bright side.
and it started
No,
as
don't
a
start to put the
university
another
laboratory
question
at the School of Aerospace Engineering from La Sapienza University, and the former acronym was Group of Astrodynamics for at the University La Sapienza. So the important thing about this laboratory was to do applied astrodynamics. So make the student get the students involved in space projects, and we started working on small satellites since the 90s. And these are some of the satellites that have been launched during the period of G.A.U.S.S as a university laboratory. We started for the first launch in 2000, and we used every time the GNAP rocket from Cosmotras. Only for the CubeSat, we used the maiden launch from Vega, from the European Space Agency. Then the G.A.U.S. SRL, the limited liability company, was founded in 2012. And in 2013, we had the idea of using a small satellite, precisely this one, as a carrier for other even smaller satellites. So to make this small satellite release other smaller satellites. So in 2013, UNISAT 5 was launched with 7 nanosatellites that were released. They were both CubeSat and PocketCubes. Then, less than a year later, we launched UNISAT 6 with 4 CubeSats inside. This is during the integration in Yasny. And it was just in a couple of days ago that UNISAT 6 had this birthday. It's 4 years that is in orbit and it's still working fine, and we receive telemetry 4 times a day. Then in 2016 we made the first satellite made using additive manufacturing technology. So we used a kind of plastic to do this CubeSat, which was an adapter between the CubeSat standard and the TubeSat. So we released these 2 cylindrical shaped satellites that were inside this two-pod, this adapter. And it was released from the Kibo module from the International Space Station. And then we plan to launch UNISAT 7 in 2020, our next carrier. So we have launched with UNISAT 5 and UNISAT 6 12 small satellites. You see some of them. And regarding how our activities are done in G.A.U.S., we have the launch services department. We have the design and manufacturing for subsystems of all the satellites that we do. And we do ground operations of our own satellites and other satellites, user satellites, client satellites. We do a lot of space debris and astronomy research, and also we do mission analysis for our next projects. Okay, so this is another nice thing to say, is that we delivered in orbit one of the first prototypes of the Spire global constellation. So one of the first satellites that were sent in orbit to test the feasibility of the constellation was launched by UNISAT 6. You can see this image while the people containing the Spire satellite was integrated inside our UNISAT 6 carrier. And now Spire has a constellation of more than 81 satellites, CubeSats in orbit. This is the some of the pictures of the integration of the two-pod and its transportation to Japan for its later transportation to the International Space Station, and then the release through the Kibo module. You can see here some images that were taken by astronauts during the release of the two-pod. You can see here where it's getting far from the deployer. And we have also, as I said, we do research on space debris, and we have an automated observation facility for space debris in the G.A.U.S.S belt. And we, one of the research was to actively monitor the descent and the re-entry of the Chinese space station. And we took this nice picture that was reported in many international news. And we also forecasted the correct re-entry time for the Chinese space station. This is a nice picture of our automated facility for the observation of space debris. So, first question, what are G.A.U.S. technological achievements so far? What have we done in the hardware department? So, we have developed several subsystems for our own satellites. And this is really important to get our project I will talk about later on. So we have developed two kinds of onboard computers, AAS and Hercules. They both fit a CubeSat, and they are quite different in terms of functionalities. But they are AAS has an extensive flight heritage, and Hercules is being tested right now. That will be using UNISAT 7. We have also developed several Uhf Radios, and we have two kinds of radios. The difference is the transmitter power output. And we also have a dual radio configuration. Then we have designed also a Uhf radio, this one, for ground support equipment. So it's like a dongle, a USB dongle that mimics an entire ground station in your fingertips. We have developed this year a GPS receiver for LEO orbit, and we will test it in orbit in UNISAT 7. And we also do complete structures for nanosatellites, and we do automated ground station for tracking our satellites and clients' satellites. Regarding the services, we do space mission analysis. We have also we are building now an ISO 7 certified clean room to do assembly integration and testing operations. We do complete satellite design, and we do all the services that are needed to design satellite, so test, ground station data services. So then we came up with this question. What are the current user and scientific demands in the remote sensing community? So we started researching what our friends, experts of the Earth Observation Department thought about their issues. So they told us that they needed more affordable, more fresher and more quality-driven and more flexible Earth observation data. So we now are in the middle of a perfect storm, we could say, because we have now, for the Earth observation, we have new investors, aggressive investors looking for good projects in this field. We now have also reusable launchers, as you know. We got new computing, cloud computing, that can do a lot of very tough calculations in a very short time. We have integrated artificial intelligence and machine learning, hardware-based computers. We got also new data, new type of data, data paired with other data synchronized with other data. And we also have the blockchain tools that is really important for security. So the barriers to access to space are falling away. The technology innovation now allows lean satellites. The demand for daily fresh data is really increasing. And now there are a lot of powerful autonomous onboard data processing capabilities. And this is really important to get something done for the EO market in space. It's a fast-growing market, the Earth observation. As you see here, we have these are values for 2027 forecasted by Euroconsult, and the value-added service market will be 5.7 billion, and the upside scenario will be 9 billion. And this is driven by a mix of defense and new commercial markets, and it's supported by the arrival of new constellation operators. And one of the service areas that are really worth looking at is the support of high-frequency change detection. So looking for changes in data with a really high frequency. And as you see, 70% of the future demand for launching will be for constellation. You can see here that from since 2018, these values skyrocketed thanks to the demand for existing constellation, like Planet Labs. They plan to have 155 CubeSat in orbit. Now they have more than 355. So what is the natural next step in the Earth observation field? The remote sensing missions using CubeSat. Why this? Because we can reduce the overall cost of the constellation while providing similar scientific results as bigger mission. We can reduce the spacecraft launch costs. We can do joint operation with bigger EO missions, and we can also use CubeSats, if there are many of them, in orbit as data relays for downlink. So, what are the challenges of the market in the remote sensing? We have typically cross-sensor and calibration issues between different type of data. We have the total cost of ownership of Earth observation constellation. We have a huge cost of large amounts of data. And we have typical incompatibility of data from different sensors. And also to be, you have to enter this market, you have to be competitive and differentiated in the global remote sensing market. And you have to look at also the trade-off that govern the existing satellite sensors, because that's the technological limit. So we thought, what would our next step be? So our next big project and maybe bold project is the Virtus constellation. So what we want to do? We want to do remote sensing. We want to do what Amazon did for cloud computing by creating a virtual Earth observation platform. So what this constellation that we are designing offers? We offer access to a virtual user configurable constellation of Earth observation satellites, allowing customers to scale and grow their business according to their needs. So our infrastructure as a solution will increase sensor consistency by using, this is really important, a multi and hyperspectral Earth observation payloads on a single platform. So inside the platform that we will send in orbit, we will have two payloads, one for multispectral Earth observation for remote sensing of just 7 bands, and then another just dedicated for the hyperspectral. And in this way, we will reduce the overall cost through access to a virtual constellation, and we will have our data that will be cross-calibrated against existing remote sensing platforms that are used now as a standard in the scientific community. So, we also have other benefits. We will pair the data that we'll gather with secondary sensor, like AAS receivers. Then our data will be dependable. It will be a very flexible service for Earth observation, you will have complete control over your data. You will have sensor consistency by doing cross calibration, and the overall platform cost will be a low-cost one, given our heritage as a small satellite manufacturer, and we will be able to scale the resources as required, and it will be rather easier to begin with. So every data owner will be able to configure his virtual constellation based on several factors. This is what makes the constellation virtual. They will be able to choose among a number of satellites available. They will be able to choose about multi or hyperspectral data. They will be able to choose the number of spectral bands available, and also the ground sample distance that they need. So if they need more resolution or less resolution, then they will be able to choose a geolocation, so a geofencing for the data. So if they just need data for Europe, they will have a price for that. They won't need to have the whole data of one satellite. You will have the choice of choosing the type of targets. So if you need data for basins or urban villages, vegetation or mining, and the data freshness will be another feature and a factor for the price. The data update, also the data pairing with secondary information, like the one that we gather through AAS receiver. Then the option to store data offline, and this is very important, the compatibility with existing RS tools. So the tools that are typically used in the scientific community will be compatible with our data. So this is the configuration, the preliminary configuration for our platform. It will be a 6U customized structure. It will have, as I said, two payloads, one multispectral and one hyperspectral. The multispectral will have 7 bands, and the hyperspectral will have 154 bands. There will be a software-defined radio receiver for AAS. We will have also a low-thrust engine for orbit housekeeping maneuvers. Then we will use our technology for the onboard computer. We will use our technology for the GPS and the radio. Then we will have S-band and X-band transceiver, one for data relay to ground and one for inter-satellite link. Then we will have an ADCS, very precise, to get the images well done, and we will have deployable solar panels. This is some information, detailed information about the multispectral payload. It's from our technical partner, Simera, and it's a new technology because it uses a sensor based on time and delay integration. So this is really important because you get a very good dynamic range even with a small form factor like this and a small aperture of 95 millimeters. And it's possible to get around 5 meters of ground sample distance at 500 kilometers and with a SWOT of 19 kilometers. And it will also have flash storage to have a strip of around 275,000 square kilometers memorized in the flash memory. So this is the estimated signal-to-noise ratio for the 7 spectral bands, which is in line with Sentinel-2, and it's plotted against the input reference radiance with a number of TDI stages optimized for the signal-to-noise ratio. So the use of this technology, TDI, will enable us to get very good results based on a nominal performance that we have with Sentinel-2. About the hyperspectral payload, it will be always provided that by Simera Sense. It will be as well a push broom imager, and it will have a digital TDI sensor. It will have a little less GST, about 10 meters, with a 41 kilometers watt. And the optical field of view will be about 2.4 degrees. So this is really important because this is what we will do in order to have our data compatible with the tools existing, the existing tools available for the scientific community. So we will characterize our data using transfer function to have compatibility with the data provided by Sentinel-2 and Sentinel-3. So the MSI for Sentinel-2 and OLCI for Sentinel-3. Another technical partner will be the one that will provide the low trust engine. So it's an Italian startup from the University of Padua, and it's called T4I, and it will provide us with a low trust engine based on magnetic enhanced plasma technology. It's a very small form factor, 1.5U. You can see here inside the chassis of a 6U. It has a quite good specific impulse, 700, 800 seconds, and it's, as you see here, it's a low trust. The propellant uses solid iodine. And another technical partner will be CubeSat. It will provide the 3-axis ADCS for control and pointing during operations and during detangling. It will have also a star tracker, 3-axis magnetometer, fine sun and earth sensor, a low power star tracker, and also a quite big reaction wheels. Another technical partner really important to get the mission done the right way is Craft Prospect, which is a UK-based startup. They work on deep learning algorithms, and they will lead the development of the onboard data processing capabilities. So they will develop the integrated neural network core, which will be based on FPGA hardware and deep learning algorithms. So this is really important because we will be able to immediately discard data which doesn't respect given quality parameters. And in this way we will reduce data downlink to Earth, and we will make sure that only meaningful data is processed at ground. You can see here the 3 colors. This is a simulation of the deep learning algorithm that we are going to use. And the green color stands for clear. So here we will take good images. Blue stands for partial coverage, and red stands for cloudy. So all this part of the image will not be downloaded if we don't override this system. So if we are doing some kind of, or a user needs some kind of data on clouds, we will be able to gather that. But usually, by default, this will be discarded. About the constellation design, this is a simulation of what we are now thinking about. With the access from our G.A.U.S. headquarters of 4 satellites, and we want to start with 2 first technological demonstrators, and then add up new platforms in orbit. So another important question that we came up with is how do we efficiently shape the initial relative geometry of the constellation? So we resumed a project that we worked on, and it's called SATCAR, which is means satellite carrier. So this is an autonomous vehicle to insert nanosatellites in orbit. It uses a high-thrust, chemical, high-performance green propellant propulsion system for fast maneuvering. It has a high boarding density because it is designed to host 50 CubeSat 3U. It is specifically developed to create phased CubeSat constellation, and CubeSat insertion can be phased over the same initial orbit, and the typical mission profile is will last 7 days, and it will use commercial off-the-shelf components to reduce the overall mission cost. And the platform will be adaptable for several launch vehicles. So this is some more rendering of our SATCAR project. You see here the main high thrust chemical engine, and then we have cold gas thrusters. And then we have here some characteristics. So the platform mass without payload will be 240 kilograms with 200 kilograms of payload, so 50 G.A.U.S.S deployers filled with 3 CubeSats. And the total platform mass will be 440 kilograms. And the control system will be based on strap-down inertial navigation system. For the propulsion system, this is really important because we wanted to use this new type of green propellant. So we will use the LMP103S, which is a green propellant, monopropellant, based on ADN. And it will give us a thrust of around 50 newtons. And we calculated that the total required impulse will be around 100 meters per second. And we will also have for ADCS, we will have cold gas microthrusters filled with nitrogen from a fuel tank. And we will use a chemical battery for the power system. So why we wanted to switch from a typical monopropellant, which is hydrogen, to a green propellant? Because let's see what hydrogen is. It's toxic and carcinogenic. It's highly toxic for the environment. It requires complex safety procedures, is very, very sensitive to air and humidity. It can be transported only by land or sea. There are several regulations, international regulations that forbid to take it on board the plane. It has a lower performance compared to the green propellant, and it has a lower density, so a lower volumetric specific impulse. While the green propellant has increased performance based on its typical specific impulse and propellant density. There is a simplified handling during fueling, so you don't have to dress up or to take special measures while refueling. There is no need to have a complex propellant transportation. So we will have a reduced environmental impact, reduced cost because of this, and we will have also increased responsiveness. So if we have to fill up the tank in a matter of days, it can be done, while with the hydrogen you have to respect a schedule of safety. And then we will have more piggyback opportunities because typically hydrogen is not compatible with some kind of piggyback modules. So this is some detailed info about the difference between hydrogen and the green propellant based on ADN. This is a typical launch profile for SATCAR. So we get at point 1 the injection into orbit by the launch vehicle. Then we have the SATCAR separation from launch vehicle. Number 2, we have the circular orbit and the first release of the first group of CubeSat. Then we have the transfer into a phasing orbit and the SATCAR flying by the phasing orbit. Then we have the SATCAR transfer back into circular orbit to get the phasing done, and the separation of the second group of CubeSats here. So, about the status of the project, Virtuous Constellation will soon enter the seed phase. So we are looking for investors right now. We have several, we found a lot of interest in the Earth observation community about this project. And we will have technology demonstrators for the upstream, and for the upstream we will have the first 2 6U platform that will be launched with our own Unisat carriers within 2 years. For the midstream, we will have our design for the ground station upgraded, and we will have the acquisition of new ground stations in order to be able to have a higher throughput of data from the platform. And then for the downstreams, we are now selecting the data processing and the distribution partners. So now we are also looking for public and private financing for the conclusions. So virtual constellation is our own idea, G.A.U.S. idea for a novel EO CubeSat constellation. It's a constellation able to provide data currently unavailable from existing players. The data access is totally configurable by the user, making the constellation virtual. And the project is being developed with renowned experts of remote sensing research. So this concludes my presentation, and I thank you very much. If you have questions. Yeah.
Thank you for the presentation. I found it really interesting. I mean, I really believe that CubeSats are that's going to be a big thing soon. I work for communication system, and one of the activities we do is the design of mission control systems. And when I see a constellation of so many satellites, I'm wondering, what have you considered for the monitoring and the processing of so much data? Because you already mentioned the onboard processing, what will allow you to select really the data, reduce the downlink. But can you rely on a classical standard mission control system for having such constellation? Does the solution already exist, or do you need to develop something new?
Thank you. So this is a good question, because the bottleneck of the constellations, Earth observational constellation, also important constellations. There was one which was acquired by Google, but now it is not used anymore, and Google paid $500 million for it. The thing is that you have to be to have a viable product that can be then sold. So the important thing, first of all, is the price of the image by square kilometer. So you have to be competitive in this way. To be competitive on this, you have to downlink a lot of data. To have this, we will have a very a new type of X-band transceiver on board the platforms. So paired with a reduced downlink based on the deep learning algorithms and the use of multiple ground stations all over the world, we think that we will be able to download as much data as the sensor is able to provide. So this is the first bottleneck that is really important to tackle. Then the second one will be data processing. So we will have to be very smart in the data processing of raw data that we acquire from the satellites. So we will use typically the new cloud computing features that are available. Because using cloud computing, you will be able to get through a lot of data more efficiently and faster than using a typical single structure for data processing. So this is what we are thinking about. This is what we saw. It was a main limitation of other competitors' constellations. Okay, so I think other questions.
Thank you.
Thank you.